In my previous video, I showed how we could use the concept of a counting unit called a box to count up large quantities of bolts. We set the quantity to equal the number of bolts in 1 kilogram. Now that number didn't come out to be a nice round number. It was 237 bolts. And we wouldn't really expect it to be a nice round number since it's based on a nice round mass. Nevertheless, it could be used to count up large quantities of bolts, like in the example where we needed to fill an order of 25,000 bolts. In the hardware analogy, we were allowed to go from a measurement of bolts in grams, quickly convert that to the quantity in boxes, which was our convenient counting unit. And then if we did want to go to quantity in pieces, we could also do that too, using the fact that 1 kilogram of bolts would equal 1 box, and 1 box would contain 237 bolts. Chemists devised a similar method of counting atoms once the relative masses of the elements were known. Remember, each element's atoms have a different mass because they have a unique number of protons, neutrons, and electrons. The electrons contribute very little mass to the atoms, however. Initially, hydrogen atoms were used as the standard, since it's the least massive element. The counting unit for chemical quantities, like our box in the hardware analogy, is called a mole. The quantity that we call a mole was initially defined as the number of hydrogen atoms in a 1 gram sample. This number is called Avogadro's number, and it's precisely been determined as equal to this long string of numbers. You can see that it's an incredibly large number. This version has 9 significant figures. We follow those 9 digits with 5 sets of 3 zeros. How big is this number? A 1 followed by 3 zeros is 1,000. Followed by 6 zeros is 1,000,000. By 9 zeros is 1,000,000,000. 12 zeros is 1,000,000,000,000. 15 zeros is 1,000,000,000,000, 18 is 1,000,000,000,000, and we're all the way up here at sextillion in the case of Avogadro's number. So what does all this mean? A mole of hydrogen, remember the number of atoms in just 1 gram, contains roughly 602 sextillion atoms. It's an enormous number. Because it's so big, we almost always write it in scientific notation. The 4 significant figure version is 6.022 times 10 to the 23rd power. Again, you can think of this as 602.2 sextillion atoms in a mole. Some things that are useful to know about Avogadro's number and the mole unit. First of all, the word mole seems a little bit strange. It comes from the Latin word mole, which means a lump or pile. You can think of it as a special pile of atoms that always has a certain quantity. It's not a nice round number because it's based on mass, just like our boxes in the previous example were based on mass. Remember, the initial meaning of a mole was the number of atoms in 1 gram of hydrogen. The mole unit can be used to count up anything, but it's most useful to count up atoms, molecules, or formula units in a chemical sample. The mole unit can be used in the same way you would use a dozen to count up donuts or eggs or some larger quantity that you're interested in. 12 donuts would equal exactly 1 dozen. 36 donuts would equal exactly 3 dozen. And you could also have an uneven number, like 75. 72 donuts would be exactly 6 dozen. 75 is a little bit more. It works out to be 6.25 dozen. Unlike the value of a dozen, Avogadro's number is incredibly large. A mole of marbles, again, that would be 602 sextillion marbles, packed together would be as big as the entire Earth. It's hard to fathom how big this number is. Imagine if the room you were sitting in was filled with marbles from floor to ceiling. That would be a lot of marbles. Now imagine the building you're in. Maybe it's a house or a school, completely filled with marbles. It's a lot of marbles. That's not even close to the number of marbles that would be in 1 mole. And remember, this is based basically on the amount of hydrogen atoms in just 1 gram. So we've established that Avogadro's number is an incredibly large number. But because atoms are so tiny, a mole of atoms or a mole of molecules is quite manageable. In fact, it could sit on your desk right now. The current day standard for the mole has been changed slightly. It's now equal to the number of atoms in exactly 12 grams of carbon-12. Remember, isotopes are named by their mass number. This is the symbol that we might use for carbon-12. Carbon's atomic number is 6. Every atom of carbon has 6 protons. Carbon-12 then would also have 6 neutrons to get to a mass number of 12. Luckily, this new standard doesn't change things very much. 1 mole of hydrogen atoms, again 602 sextillion hydrogen atoms, has a mass of 1.0078 grams by the new standard. It doesn't change things very much. This version has 5 significant figures in the measurement. It still equals essentially 1 gram. Your periodic table might only have a 4 significant figure version of this number. Many periodic tables will list the value as 1.008 grams, and some might even list it as just 1.01 grams.